Hey guys, we're back with part 3 of section 4.4, graphing with asymptotes. Now, in the last two sections, we went over the definitions of horizontal and vertical asymptotes, how to find them and determine what they are. And with horizontal asymptotes, we spent quite a bit of time evaluating limits as x approaches infinity. So, evaluating infinite limits, where we use the tower of power to determine the highest dominating term in order to calculate those desired limits and find our horizontal asymptotes. But now, in this part, all we are going to do is go over this example on graphing with asymptotes. So we're going to take this function, and then we're going to do the exact same process we've been doing in the earlier sections of chapter 4, when we were graphing functions, using first, second derivative tests, knowledge of derivatives, things like that. And then we're just going to tack on adding asymptotes to the situation. All right? So, suppose the situation, we want to graph the function f of x is equal to 1 plus x divided by x minus 4. Now, first up, we want to find the asymptotes. Now, let's find the vertical asymptote first. So we have our f of x is equal to 1 plus x over x minus 4. Now, I find when you're trying to deal with situations like this, find a common denominator and combine the functions makes it easier if you just have one term. So this is equal to x minus 4 plus x over x minus 4. Well, that's just equal to 2x minus 4 over x minus 4. All I have done here is combined the two fractions into one. I just find it's easier to work with it that way. Now, let's find the vertical asymptote. Now, what is the vertical asymptote? Well, we have a vertical asymptote at a point x is equal to c if the limit as x approaches c from the left or right is equal to plus or minus infinity. So, if we look at this function, we can kind of guess that we think there's going to be a vertical asymptote at the point x is equal to 4. Why? Because we have an x minus 4 in the denominator, so when you plug in 4, it's division by 0, breaks the function. Now, it could be whole, could be a jump, so we still have to check. So we think it's at x is equal to 4. So let's take the limit as x approaches 4 from the right of 2x minus 4 over x minus 4. Well, we plug in 4 into the numerator, then we get 8 minus 4 over the limit as x approaches 4 from the right of x minus 4. Well, that's just going to become 4. So we have 4 divided by the limit as x approaches 4 from the right of x minus 4. Now what happens when we evaluate this one-sided limit right here? Well, we're punching in numbers that are really close to 4 but are slightly bigger than it. So the numbers in the denominator are going to be positive, but they're going to get arbitrarily small. So what does that tell us? That this limit as x approaches 4 from the right is going to equal infinity. Excellent. So that tells us we have a vertical asymptote at x is equal to 4. Man, we're off to a good start already. So we know we have a vertical asymptote at x is equal to 4, but that tells us the behavior of this function as we approach 4 from the right. Let's just go ahead and check the limit as x approaches 4 from the left, shall we? Just to see the change of behavior. Well, we do the exact same process. Press 4 from the left. Well, on the top, because that's continuous, we can just plug it in. That'll become 4 divided by the limit as x approaches 4 from the left of x minus 4. So it's the exact same setup, exact same situation. But the difference is now we are plugging in numbers that are slightly less than 4. So the denominator is going to be all negative numbers in that sequence. But they're negative numbers that are tending to 0. So the denominator is going to get arbitrarily small, meaning the whole thing is going to get arbitrarily big, but in the negative direction. So the limit as x approaches 4 from the left is negative infinity. All right? So this doesn't change our information. We still have a vertical asymptote at x is equal to 4. We know it runs into that barrier. However, now we know if we come up from the left, the function dive bombs towards negative infinity, and if we come at it from the right, it skyrockets off towards infinity. But we still have our vertical asymptote is that x is equal to 4. But now, we want to find the horizontal asymptote. Don't feel like spelling the word asymptote. All right, how do we do that? Well, to do that, we evaluate the limit as x approaches infinity of our function f of x, which is equal to 2x minus 4 over x minus 4. Now, how do we evaluate this limit? Well, what we should do is multiply this by 1 over x divided by 1 over x. Why, you may ask? Because x in this fraction is the dominating term. It's the one that's going to go to infinity the fastest compared to the constants. So that's the one we want to divide every term by. So this is equal to the limit as x goes to infinity of 2 minus 4 over x divided by 1 minus 4 over x. Because the x's here are going to cancel, and then the 4's are going to be divided by x. Remember, what the thing in the blue is doing is just dividing every term in the fraction by 1 over x, is dividing it by x. That's it. It's just dividing it by x. All right. Now, here, because I want a little bit more room, this is equal to the limit as x approaches infinity of 2 minus the limit as x approaches infinity of 4 over x divided by the limit as x approaches infinity of 1 minus the limit as x approaches infinity of 4 over x. What did I do? I passed the limit to every term. That's all I did. Properties of limits, right there. Now, this first term, right here, this limit as x approaches infinity of 2. What's it going to converge to? Well, that's just going to go to 2. It's a constant. It's not going anywhere. Now, what about this term? The limit as x approaches infinity of 4 divided by x. Well, the 4 is fixed, but we are dividing it by bigger and bigger and bigger numbers. So this whole thing is going to go towards 0. So we get 2 minus 0 over 1 minus 0 for the exact same reasoning as above. Well, what's 2 minus 0? That's 2. What's 1 minus 0? That's 1. So that's just equal to 2. So we have a horizontal asymptote at y is equal to 2. So all we did here was took our guess for the vertical asymptote and then evaluate the limit from the left and the right. We saw that from the left and the right tend towards positive infinity and negative infinity respectively. And then for the horizontal asymptote, all we did was found the dominating power, which was x in this case, divide every term by it, simplify, evaluate the limit at each term in the numerator and the denominator, recognize that these terms right here go to 0, and we're left with this, that's just equal to 2, so we have a horizontal asymptote at y is equal to 2. So, that's our asymptotes. Alright? Now, let's move on to the next part. We want to find where f is increasing and decreasing. Alright? How can we do that? Well, to do that, we need to do the first derivative test. And to have the first derivative test, what do we need to have? Well, we need the first derivative. So, if f of x is equal to 1 plus x minus 4 over x minus 4, then f prime of x is equal to 0 plus, since we have one function divided by another function, or a quotient of functions, we need, you're right, the quotient rule. So we have the bottom times the derivative of the top minus the derivative of the bottom times the top all over the bottom squared. Why is there 0 here? It's because the derivative of 1 is 0. Well, this is just equal to x minus 4 minus x over x minus 4 squared, which is just equal to negative 4 over x minus 4 squared. Now, to find where it's increasing or decreasing, we need to determine the critical points. Now, where do we have critical points? Where the derivative is equal to 0 or where the derivative is not defined. Now, let's look at this derivative, negative 4 over x minus 4 squared. This function right here is never equal to 0. Why? Because the numerator is equal to negative 4. It's a constant. It's never going to be equal to 0. So we do not get any critical points from the derivative being 0. However, if we notice in the denominator, we have this x minus 4 squared term. So what happens when we plug in 4? We have a 0 in the denominator, hence the derivative does not exist. So at x equal to 4, f prime of x does not exist. So we have a critical point at x equal to 4. Now we have a critical point. Why do we want the critical points? Because when we have all the critical points in our hand, we can determine where f is increasing or decreasing. Because if the critical points are the only place where the function is not increasing nor is it decreasing. So let's build our little number line now. We only have one point to worry about, and that's at x is equal to 4. So now we need to pull out a couple candidates. Let's pull out 5, and what's another fun one? Let's just do 1. I like 1. So actually I'm going to change that size so it's like readable. So that's 5, and that's 1. Those are our test values. Why do we want these test values? Because they determine the sign of the function on that entire interval. We figured out everywhere the function does not have a sign. So all that is left is for the function to have a sign. And since it's continuous on these intervals, whatever the sign is at the test point, that's the sign of the function on the entire thing. All right? Okay. So we have our test values. Let's figure out f prime of 1. So we have f prime of 1. Well, that's equal to negative 4 over 1 minus 4 squared. Now, positive always negative, or the numerator is always positive, the denominator is always negative, so that tells us our function is decreasing on this interval. So from negative infinity to 4, this function is decreasing because the derivative must be negative everywhere on the interval. Now, what about f prime of 5? Well, that's equal to negative 4 over 5 minus 4 squared. I'm just going to write that's less than 0. But for the exact same reason as above, this is also less than 0 because the numerator is always negative, the denominator is always positive. Negative divided by positive is negative. So that tells us on this interval, the function is still decreasing. So we can tell that on the interval 4 to infinity, the derivative is still negative. So this derivative is negative everywhere except x is equal to 4 where it's not defined. So it can't be negative there. Well, can't really have a sign if you're not defined. You know what I'm saying? All right. Man, quarantine's getting to me. Okay, so now we have this, but we want to figure out where f is increasing and decreasing. Where is it increasing? Well, nowhere. The derivative is not positive anywhere, so this function is decreasing everywhere. So we can just put in a nowhere, none, wherever you want. Just indicate that we are not increasing anywhere. What about decreasing? Well, decreasing, we're decreasing everywhere. So we just put negative infinity to infinity. Now, pause. Why is that not right? Why are we not decreasing on the entire interval negative infinity to infinity? That's why. X is equal to 4. At x is equal to 4, the derivative does not exist, so it does not have a sign there. So we're not decreasing on negative infinity to infinity. What we're actually doing is decreasing on the interval negative infinity to 4, non-inclusive, union 4 not inclusive to infinity. That is where we are actually decreasing. So we took the derivative, found our critical points, tested the intervals, and determined where we were increasing, which was nowhere, and then where we were decreasing, which is everywhere but the number 4. All right? So that's how we've determined where f is increasing or decreasing. Okay, let's go on to the next part. Good Lord. Okay, so now we want to find the relative extrema, i.e. relative maximums and relative minimums. Now you guys can see why, when we started this semester off, when we were in class, I used slideshows all the time. My handwriting is awful. That says relative maximum, relative minimum, if you believe me. But we want to, okay, my little brother keeps texting me. Leave me alone, John. Leave me alone. Especially because he's not being helpful. It's his birthday today, and, you know, I'm taking him over to dinner and stuff because we're quarantined. I can't take him out. It's his 21st, so, you know, just, I'll deal with him later. Okay, so we want to graph this function. We want to find the relative extrema in this step. All right. Recall this from the previous part. We had this little thing where x is equal to 4, and we were decreasing on this interval. We kind of went flat here, and then we were decreasing on this interval. We didn't really go flat there, but whatever. So we had this. The first derivative tells us we have a relative maximum if the function is increasing, levels out, and starts decreasing, or a relative minimum where the function is decreasing, stops, and increases. Do we have either of those here? No. No, we don't. So there are no relative extrema. This is what we call boring. But no, it's not. It's actually quite fascinating. The idea that there are no relative maximums and no relative minimums, but it still has a discontinuity at x is equal to 4. That's quite fascinating. So there are no relative extrema for this problem. All right? But that does not mean we're done. Now it's time for concavity. Alrighty. With concavity, what do we need? Well, to determine concavity, we need a second derivative, the rate of change of the rate of change of a function. So we need the second derivative. But recall the first derivative, which is equal to negative 4 over x minus 4 squared. But that's also just equal to negative 4 times x minus 4 to the negative 2, right? You'll see why in a second why I rewrote it like that. Makes it easier to differentiate. So that's our first derivative. Now our second derivative, f double prime of x, well, that's just equal to 8 times x minus 4 to the negative 3. Just the power rule, which is equal to 8 over x minus 4 cubed. So that is the second derivative of our function. Now, we need to determine where the concavity can change. And the concavity can change where the second derivative is equal to 0, and where the second derivative does not exist. So where is the second derivative equal to 0? Well, it's a fraction with a constant in the numerator. That means it's never 0. Fun. All right. Now what about where f double prime of x does not exist? Where do we have a discontinuity? Well, we have a discontinuity when x minus 4 cubed is equal to 0, or when x is equal to 4. Noticing a pattern here. So at x is equal to 4, we have our discontinuity, our jump. So if it's going to change concavity, at x is equal to 4, that's where it's going to happen. So at x is equal to 4, there is no concavity. Now, let's pull out our test regions again. Here, let's pull out x is equal to 5 for our test, and for this left half, let's pull out x is equal to 1. Now, f double prime of 1 is equal to 8 over 1 minus 4 cubed. Now that's actually less than 0. Big shocker. Everything's been negative so far. So actually, on this left interval, we are actually concave down. Second derivative is negative, so we're concave down. But now what about f double prime of 5? That's equal to 8 over 5 minus 4 cubed. Now wait a second. That's a positive number divided by a positive number. That's greater than 0. Finally, some positivity in our lives. So, on this interval right here, we're actually concave up. So, to write this in interval notation, we're concave down on the interval negative infinity to 4. We're concave up on the interval 4 to infinity, everything non-inclusive. Why? Because we can't include infinity in these intervals. We can't include x is equal to 4, because at x is equal to 4, the second derivative does not even exist. Cool. All right. Now, let's move on to the next part. Find the inflection points. So what we just calculated is this little handy chart. If x is equal to 4, the left-hand interval, we are concave down. Left interval, we are concave up. Now, to be an inflection point, it has to be where the concavity changes, right? So that's what it means to be an inflection point, where the concavity changes. So, and what do you know? At x equal to 4, the concavity changes. But why is it not an inflection point? Well, that's because the inflection point has a second condition. F double prime must exist at the point, but F double prime of 4 does not exist. So we can conclude there are no inflection points. So you got to be careful with that. Just because the inflection changes does not mean that this is an inflection point. To be an inflection point, the concavity has to change and the second derivative has to exist at that point. Excellent. So, now, let's move on to the last but probably the most important part of this. Graph this thing. Alrighty. So, it's the exact same process we have been doing, but now we just have to include horizontal and vertical asymptotes to our process. Let's just write those guys down. The vertical asymptote is at x is equal to 4. So let's just go ahead and label our axes. We're going to do everything in 2, shall we? So 2, 4, and 2, 4. So we have a vertical axis at x is equal to 2. That means the function cannot pass that point at all. But at x is equal, or but at, I messed that up. I apologize. What'd I mess up? Take a second to think and figure it out. Yeah, I mixed up the horizontal and vertical asymptotes when I glanced at the side. That is my fault. I apologize. The vertical asymptote is x is equal to 4. This is where our vertical asymptote is. X is equal to 4. I was wondering why that was looking wrong. So at x is equal to 4, that's our vertical asymptote. Now we need to do with our horizontal asymptotes. That's at y is equal to 2. I'm going to change the color. Let's do blue on that one, shall we? So our vertical asymptotes in red, our horizontal asymptotes in blue. Now we need to take the rest of this information that we have. We know we're decreasing everywhere except the vertical asymptote. So that means on this side, we're kind of going in this direction. We're kind of decreasing here and we're kind of decreasing there. So we know that. But we also know we're concave up in here. So our concavity is facing up in this region and down in this region. So using that information, we can kind of sketch that this graph is going to look something like this. We're decreasing. We're also concave down. And in this interval, we're decreasing, but we're also concave up. So concave up there, concave down here. Remember, not looking for any Picasso work here. All I'm looking for is when you graph these things, do you understand what all of this information means? Can you take all of this information and translate it into a graph? All right? So, there's nothing fancy with the graphing with asymptotes. It's the exact same process as before. We just tack on the horizontal and vertical asymptotes to it. Alrighty. So that's all I have for you guys on section 4.4. And I know that's all I have. This is my third video on it. So that wraps it up for section 4.4. Tune us next time where we will cover section 4.5 called L'Hopital's rule. Alright guys, I will see you next time where we will have more fun with math.